Hello everyone. My name is Shudhanshu Sarkar. I'm assistant professor in the Department of Electrical Engineering at Narula Institute of Technology. So the lesson plan of circuit theory network. This is lecture two on the couple circuit. So this couple circuit is in module 4. So in this module 4, I'll discuss few topic of the magnetic couple circuit. So that's all about the course outcome of this circuit theory network subject. So magnetically coupled circuit. What is magnetically coupled circuit? I already described in the last lectures. Today I'm also going to talk about these two subtopics. One is coupling coefficient and second one is dot determination. So in the coupling coefficient, please follow the first lecture, go through the first lecture so that you can understand very easily about this coupling coefficient and the determination. So coupling coefficient is represented by K. It is measure of the magnetic coupling between two coils. Range of K is K value is greater than equals to 0 and less than equals to 1. K equals to 0 means the two coils are not coupled. K equals to 1 means the two coils are perfectly coupled. So please try to remember the range of K is 0 to 1, maybe 0, maybe 1, and maybe in between the value. And the value of K is 0 means two coils are not so this is the value, the range of this coupled circuit. Then if it is K equals to 0, for K equals to 0, for K equals to 1, for 0 what will happen? Not coupled, but if it is 1 then perfectly coupled. You can find this type of question for MCQ type question. If the value of K equals to 1, then how it is coupled? So it should be perfectly coupled. Two coils will be perfectly coupled. If it is 0, the value of K is 0. K is actually the coupling coefficient. Then it is not coupled. But if the value is less than 0.5, so what is the meaning of this? The meaning means two coils are loosely coupled. It is less than 0.5. So this is also important. Less than 0.5, greater than 0.5. For less than 0.5 is loosely coupled. For greater than 0.5 it is tightly coupled. These are the four property we have to understand, solve the circuit or to the realization of about the coupling coefficient. So the range of K is greater than equals to 0, less than equals to 1. We can consider the value K equals to 0, K equals to 1, K less than 0.5, K greater than 0.5. K equals to 0 means two coils not coupled, K equals to 1 means two coils perfectly coupled. K less than 0.5 means two coils are loosely coupled. But if it is greater, K equals to greater than 0.5 means the two coils are tightly coupled. So these are the properties we have to remember to understand the coupling coefficient. Now K depends, so this K always depends on the closeness of two coils, their core, their orientation, and their winding. So what are the most important thing we have to consider? The value of K depends on which parameter of the coil? So obviously there should be two coil. Secondly, their core, it depends on their core. Thirdly, their orientation, and fourthly, their windings. These are the four parameters we have to remember always. It depends on the closeness of two coils, their core, their orientation, and their windings. The coefficient of coupling K is given by, is the equation, K equation, that is given by capital M divided by root over L1 into L2. So you can say that M, so this is actually the relation, the K equals to the mutual inductance divided by root over of self inductance of both sides of the coil. So you can say in modified form that M is equals to, you can say like this, M is equals to K into root over L1 into L2. So mathematically we can define K is equals to M divided by root over L1 and L2. Root over L1 and L2. So that M equals to K into root over L1 to L2. Now we're going to talk about the dot determination. So dot determination to determine polarity of mutual induced voltage. Why it is required? It is required to determine polarity of mutual induced voltage. So why it is so important? Number one is it is required to determine the polarity. Polarity of which? Mutual inductance. The polarity of mutual induced voltage. It is required to determine polarity of mutual induced voltage. Mutual induced voltage is very important. Next, the dot is placed in the circuit at one end, each of the two magnetically coupled coils, to indicate the direction of the magnetic flux if current enters that dotted terminal of the coil. So first one is required to determine the polarity of mutual induced voltage, and second one is a dot is placed in the circuit at one end, each at one end, each of the two magnetically coupled coils. So where it is placed, dot is placed at one end, each of the two magnetically coupled coil, each of the two magnetically coupled coil, to indicate why the direction of the magnetic flux. Indicate what? To indicate the direction of the magnetic flux if current enters the dotted terminal of the coil. Yes, so this is the current enters the dotted terminal of the coil. So these are the basic requirement of dot determination. Now look the figure, magnetically coupled figure. There are two dots, one in the left hand side, one on the right hand side, one from the current entering into the circuit I1, and from the right hand side secondary terminal current entering into the circuit, it is I2. This is coil 1, coil 2. So here the voltage of the primary end is V1, current I1. The voltage of the secondary is I2, voltage is V2, current I2. And the self flux is phi 1 at the primary side, and secondary side is phi 2. The mutual flux is phi 1 and phi 2. That's all about the circuit. Now, dot convention is started as follows. So these are the things we have to remember. If a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage in the second coil is positive at the dotted terminal of the secondary coil. I think it is clear. It's written very clearly. I already explained this, that if current enters the dotted terminal, if it enters the dotted terminal, then what will happen? If it enters the dotted terminal of the coil, the reference polarity of the mutual voltage. Reference polarity of the mutual voltage. What? The reference polarity of the mutual voltage in the secondary positive. Reference polarity of the mutual voltage in the secondary is positive at the dotted terminal of the secondary coil. At the dotted terminal, where the dotted terminal of the secondary coil. Conversely, dot convention may also be stated as follows. How? If a current leaves the dotted terminal of one coil, it leaves, the reference polarity of the mutual voltage in the second coil is negative. Just the opposite, the reverse meaning of the first point. The first point, enter positive secondary coil. If it is leave, then what will happen? If current leaves the dotted terminal of the coil, the reference polarity of the mutual voltage in the secondary coil is negative. Secondary coil is negative at the dotted terminal of the second coil. So when enters mutual voltage, reference polarity, secondary voltage negative. When enters positive, when leaves negative, secondary coil. Now let's talk about the following dot rule. So what is the rule? Rule is when the assumed current both entered or both leaves a pair of coupled coil by the dotted terminals, the sign on the L terms. And number two, if the current enters by a dotted terminal while the other leaves by a dotted terminal, the sign on M term will be opposite to the sign on the L terms. Okay. So M term sign and L term sign for the first case will be same. That means if you follow, I think something is missed here. When the assumed current both entered or both leaves the pair of coupled coil by dotted terminal, the sign of M term will be opposite for when dotted terminal leaves, but when assumed current both entered on both leaves a pair of coupled coil by the dotted terminal, the sign on the L terms. And if the current enters by a dotted terminal while the other leaves by a dotted terminal, the sign on the M terms will be opposite to the sign on the L terms. So this is the opposite of the N terms. So remember this part also, the following rule. So let's we'll try to understand these with some common example. Once the polarity of the mutual voltage is already known, the circuit can be analyzed using mesh method. Fine. You all know about mesh method. I already discussed this mesh method in circuit analysis, or you can say in theorems, circuit theory theorems chapter. Application of dot convention, example 1. The sign of mutual voltage V2 is determined by reference polarity for V2 and the direction of I1. Since I1 enters the dotted terminal of coil 1 and V2 is opposite at the dotted terminal of coil 2, the mutual voltage is M di1 dt. M di1 dt. Try to understand this part again. The sign of mutual voltage V2, the sign of mutual voltage V2, this is determined by the reference polarity for V2, okay? And the direction of I1, this is I1 towards V2. Since I1 enters the dotted terminal, so it is entering to the dotted terminal of coil 1 and V2 is opposite. V2 is opposite at the dotted terminal of coil 2. The mutual voltage is M di1 dt. Example 2. Current I1 enters the dotted terminal of coil 1. Okay, coil 1, and V2 is negative at the dotted terminal of coil 2. The mutual voltage is minus M di1 dt. So here the dotted terminal of coil 1 V2 is positive. The dotted terminal of coil 2, if the dotted terminal is in positive side, so for that case the mutual voltage is M di1 dt, but if it is in the negative side then it is minus M dit dt. Consider, look once again, current I1 enters the dotted terminal of coil 1 and V2 is the negative at the dotted terminal of coil 2. Negative at the dotted terminal of coil 2. Try to understand. Enters the dotted terminal of coil 1, current I1 enters the dotted terminal, and it is V2 is the negative of the dotted terminal, coil 2, the mutual voltage is minus Mi1 dt. I think it is clear to all of you now. And for this case, for the first one, the sign of mutual voltage V2 is determined by the reference polarity for V2 and the direction of I1. Fine. Since I1 enters the dotted terminal of coil 1, V2 is positive at the dotted terminal of coil 2, the mutual voltage. So very carefully. I1 enters the dotted terminal of coil 1. V2 is positive at the dotted terminal of coil 2. The mutual voltage is, what is the mutual voltage? M di1 dt. Here it is minus M di1. So for this case, both are in positive location. This is in positive side V1. This is in, the polarity is in positive side, so it is plus M di dt. Here positive, but this one is in negative, minus M di dt. Minus M di dt. Okay, so go to the next slide for the better explanation of this. Here, same reasoning is applies for example 3 and 4. Example 3, look, this is in positive side, this is in negative side. So v1 is minus m di2 dt. Okay, negative negative, then what will happen? Negative negative, and v1 is equals to m di2 dt. So v1 equals to m di2 dt. So if the polarity is in the opposite sign stay, then negative sign will come, same stay, positive sign will come. Now dot conversion for coils in series. Look, it is L1, this is L2. So it is in the starting point, is in the starting point. Then what is happening? This is the M mutual inductance, this is self inductance L1, self inductance L2, positive, positive. Then L equals to total L. Total inductance equals to L1 plus L2 minus 2M. Oh, sorry, plus 2M. Both are in positive sign. Series adding connection. Series opposing connection. So here, if the negative sign come here in between two inductors, then what will happen? L1 plus L2 minus 2M. So negative sign will come. Look, here it is in positive, positive. So minus 2M. Now below are example of the sets of equation derived from basic configurations involving mutual inductance. In circuit 1, solution in the given circuit, we have a voltage source plus minus DC voltage source Vs. Resistance, the current in the first loop is I1, the current in the second loop is I2. This is JA, the dot conversion. Now R1 plus R2 for the KVL, if we apply KVL in the first loop, R1 plus R2 plus JA into I1 minus Mi2 equals to Vs minus Mi2. So here the sign in the opposite position. So minus sign is coming. Now the voltage 2 minus R2 I1 I2 R2 I1 plus R2 plus R3 plus JB into I2 R2 plus R3 plus JB all in the same direction minus MI1. So it is also minus because in opposite direction the dot convention is there, that is equals to 0. So in equation 2, now move to next slide. So here look what is happening. So M will be positive for the first loop because both are in the starting point, the plus position. So R1 plus JA plus JB into I1 minus JB into I2, no problem with this opposite direction current, plus M, the same position, so plus M, I1 minus I2, I1 is coming from upward, I2 is going from downward, plus MI1, that is equals to Vs, and for the second loop, minus JB I1, no problem, so I1 is opposite direction, and I2 plus R2 plus JB minus JC minus MI1, it is in minus MI1 equals to 0. So for this case, it is in the opposite direction. So this is negative sign will come for this case. Now circuit 3, look for this case. In loop 1, KVL apply if we apply. So how to find I1? R1 plus JA minus J into I1, J into I1 minus JAI2 minus JAI2 opposite direction. So minus is coming plus MI2 plus MI2 same position starting point positive terminal that is equals to V2. For I2 current second loop minus JI1, so no problem minus JI1 because we are considering I2 in the opposite direction plus R2 same direction with I2 plus JA no issue plus JB, but this is will be negative, so minus I2 is negative because minus MI2 minus MI2 minus I1, so negative sign is coming for the opposite direction. This is negative sign, that is equals to 0. Now for circuit 4, so for circuit 4, if we apply KVL for loop 1, then R1 plus R2 minus JC into I1 minus I2 into R2 equals to VS. Because no dot is here, but dot is in this position. So minus R2 into I1 minus R2. Where is R2 into I1? This problem. I is coming from opposite side. I is in the opposite direction of I2, so minus plus R2, yes, R2 plus JA plus JB into I2, same direction, minus 2 MI2, because this is here in opposite direction, so 2 MI2 coming for inductance is equals to 0. For circuit 5, now here 3 dot is there. So for the first loop, R1 plus R2, R1 plus R2 plus JA plus JC into I1 minus R2 plus JC, R2, yes, opposite direction R2 plus JC into I2, no problem. I2 is in opposite with I1, so minus sign is coming. Now mutual inductance, how many mutual? This is M1. So first consider M1, so M1 minus sign will come because this is here, opposite direction, so minus M1 I1, no problem. Now M1, for M1 common current is there, so M1 into minus M1 into opposite I1 minus I2, I1 minus I2, no problem. Now M3 is also between these two, so this is also minus because M3 into I2, and here M2 plus I2, M2 plus I2, this is I2, that is equals to VS. Number 1, and for loop 2, what will happen? Minus I for I1, this is minus, these two will be minus R2 plus JC minus I1 plus R2 plus JC plus JB minus JD, R2 plus JC plus JD JB minus JD into I2 opposite direction, same this plus M1 I1 plus M1 I1, no problem with this, minus M2 I2 minus M2 I2 M2 I2 opposite direction, yes, minus M3 I1 minus M3 I1 opposite minus M2 opposite I2 minus I1 equals to 0. So in this way we can understand the meaning of the dot conversion, and this is the reference of this lecture. So I take the help from this internet source, and with this I take help from the circuit theory and networks books by Abhijit Chakraborty sir. So thank you everyone for watching this video. And thank you everyone for stay with me in the last half an hour. Thank you.